Hi, let's continue to talk about triple integrals in spherical coordinates. When a solid is bounded by spheres and or cones with vertex at the sphere's center, it is often convenient to use the spherical coordinates rho, phi, theta. We call that rho is the distance to the origin. Phi is the drop-down angle from the positive z-axis, and theta is the angle from the polar or cylindrical. Okay, so the relations with the Cartesian coordinates are as before, except rho is a variable now. Okay, so let me show you the other picture I have. Okay, so this is the picture. P is a point in the space, right? Phi is the drop-down angle from starting from the z-axis, so we drop down 5. Okay, and then theta is the angle. So when we project this point P to point Q on the xy plane, and then Q is the angle made with the positive x-axis. Okay, so now can you see? We have this triangle. This is our R, okay? And the distance from the point P to the origin is rho. Now you can see this red circle. Here we have here we have R, and here we have Z, here we have rho, and the drop down angle is phi. And then so you can see R is the opposite over hypotenuse. So R over hypotenuse is sine phi, right? So R equals rho times sine phi. And then Z is the adjacent. Adjacent over hypotenuse is cosine phi. And so Z equals rho times cosine phi. So far so good, everybody? Okay, now let's go down. So what are the relationship between the rectangular coordinates, spherical coordinates, and the cylindrical coordinates? So last time we already talked about this, right? So today let's continue to look at the relations. First, let's look at the relation between spherical coordinates and cylindrical coordinates. So if we're given cylindrical coordinates, how do we get spherical coordinates? Well, rho, you can see on the red triangle, rho is the hypotenuse, the drop-down angle is phi, and this is z, and this is r. So rho equals square root of r squared plus z squared. And tangent of phi, tangent of phi is the opposite over adjacent. So that is, oh, I see I have a typo here. This guy should be R over Z. Oops. Okay, sorry about this typo. Okay, now theta is still theta. So usually how do we compute the phi? Well, the phi, it depends on it's gonna be the arctangent, but it also depends on where the point is located. Okay, so if the point is, imagine phi is the drop down angle. Okay, so phi is between 0 and pi. So phi is between 0 and pi. Okay, but the point, so if the point is above the xy plane, we have the phi is between 0 and pi over 2, right? If the point is below the xy plane, then we will have our phi is between pi over 2 to pi. Okay, so that's why, but the arctangent only cover the region negative pi over 2 to pi over 2. So that's why if point is above xy plane, we use arctangent of r over z. If the point is below the xy plane, then we should use pi plus arctangent of r over z. So far so good, everybody? Okay, and theta is still theta. On the other direction, if we r we already figured out r is rho times sine phi, and z is rho times cosine phi. Theta is theta. So far so good? Okay, now let's look at the relationship between rectangular coordinates and spherical coordinates. So if we know the spherical coordinate and we want to get the rectangular coordinates, so think about what is x. Well, let's look at this picture. X is r times cosine theta, but r is rho times sine phi. Okay, so we can actually borrow these guys, borrow this relation. So because x is r cosine theta, but r is rho sine phi, so that's why x is now rho sine phi cosine theta, because that is like r. And then y is r times sine theta, so r is rho sine phi. Okay, so now y is rho sine phi sine theta, and then z is rho cosine phi. Okay, we know that. Okay, already. And then on the other side, if we know x, y, z, how do we get rho, phi, and tangent? Well, rho is the square root of x squared plus y squared plus z squared. And then the theta, tangent theta, give us y over x. And in order to get the theta, we use this guy as well. Okay, depending on which quadrants it is in when we project the points on the xy plane. Okay, so this rule also applies here. And then cosine phi. Well, we can use cosine phi or sine phi or tangent phi as you like. Okay, so cosine phi is z over rho. Okay, then is z over square root of x squared plus y squared plus z squared. And tangent phi is r over z. R is square root of x squared plus y squared plus z. When you take the cosine or arctangent, you also need to think about the range of the cosine or arctangent. Does it cover the angle? Okay, if it's not, you probably need to add pi to it. Okay. The idea is very similar to like what we do here. We need to think about the range of the arctangent or arccosine, and then you think about, oh, our phi is between 0 to pi. Do we cover those regions? And then so this is how we think about it. Okay, everybody? So let's continue. Okay, so yeah, here is the formula. Okay, we already read it about. And yeah, we can also use sine phi is r over rho. Okay, so when we were computing the surface integral, we saw a small increment d phi in the phi and small increment d theta in theta. So that will give us the area differential. Okay, let's look at this patch. Let's look at this patch. It's roughly like a rectangle, right? Let's use length times width. So what is this guy? And what is this guy? Well, think about what's sector. What is the length of a sector? So if a sector, we have the angle theta, and this is r. The length of sector equals the angle times the radius. right? And now let's use different color, then you can see which piece I mean. Okay, so let's look at this guy. What is the change of the angle? Well, the change of the angle is the phi, because phi is the drop down angle, right? You see how it changed. And then what is the radius correspond to that? Well, the radius of this angle, okay, of the points is rho. Okay, so this length of this small patch is rho times the phi. Okay, how about the other side? Well, the other side, this I thought I changed to blue color, and it is not. Is it blue now? Okay, so this we want to figure it out. Okay, so imagine those 2 points when we project on the xy plane. Yeah, you see this guy and this guy, they have the same length, right? And what is this? Well, this is actually the angle is change of theta. And what is the radius of that point? Well, the radius is r. But what is r in terms of rho? We know r is rho times sine phi. So that's why the other length is rho times sine phi d theta. So combine them together, we have rho squared sine phi d phi d theta. This is the area of this patch. So far, so good, everybody? Okay, now when we compute triple integral, at small increments, d rho in rho adds a thickness to this patch. Then the volume of the solid object is approximately the area of the patch times the thickness, d rho. So far, so good, everybody? Okay, so volume differential. That's rho squared sine phi d rho d phi d theta. Yeah, this is the hardest one. Let's review what we had before. For rectangular coordinates, so dv equals dx, dy, dz. We can change the order, of course. Okay, and then for cylindrical coordinates, we have r squared. We have r dz dr d theta. Still kind of easy. And then I would say the spherical coordinates is the hardest one. It's rho squared sine phi d rho d phi d theta. Okay. And then, do you recall the volume of a sphere with radius a? Let's set up and evaluate triple integral to find this volume. Do you remember that? So, if we have a sphere with radius a, what is the volume? Someone remember? That is 4/3 pi a cube. Okay, from the formula of a sphere, right? Okay, now let's check it out. Okay, let's actually integrate it. So now let's see. So we have the sphere. Okay, so you know sphere. This is a sphere centered at the origin. Okay, so it's x squared plus y squared plus z squared with radius a squared. Okay, so and when it cross here, this is a, and this is a as well. Okay, now let's see. We have a triple integral because we want to calculate the volume. Then we have 1 as our function inside. And then what is the volume differential? Okay, let's see again. That's rho squared sine phi d rho d phi d theta. Is that okay, everybody? And we look from the outside to the inside. Where do our theta goes? Oh, you can see, well, this region, the theta is the whole sphere. So theta goes from 0 to 2 pi. Right? So this is theta. And then how about phi? Well, look at the if it's any point there, then we look at, let's say this is the point. Phi is the drop down angle, right? The drop down angle is from 0 to pi. You don't go beyond pi because it looks like you go around. You don't go back and wraps around. Okay. Our phi is between 0 and pi, and then we let the theta goes from 0 to 2 pi. That will cover the whole sphere already, right? And how do I cover this back? You can think about it, instead of the phi going that big with this direction, you can imagine, oh, we can have our theta goes to this direction, and then when we drop it down, we drop it down until here. Okay, so we drop down our phi like this place. So as long as we let theta goes from 0 to 2 pi, and the phi, we just need it from 0 to pi. We don't need it to go from 0 to 2 pi. So far, so good? Okay, yes. And so phi is from 0 to pi. Now how about our rho? It's the whole sphere. So from 0 to, what's the radius of the sphere? A. Okay, everybody? Now let's integrate. First, let's integrate with respect to rho. So integral rho square is rho cube over 3, and then we have sine phi d theta. Well, this got evaluated from 0 to 8. Okay, so it means we plug in a, we get a cubed over 3. And when we plug in 0 is 0. So because it's constant, we can move it outside of the integral. And then we have sine b d phi d theta. Okay. All right. So next, integral of sine phi. Integral of sine phi is cosine plus or minus cosine phi. And then phi evaluated from 0 to pi d theta. Let's see. Okay, so now we have 0 to 2 pi. We plug in pi first. So cosine pi minus negative become plus cosine 0. And do you know what is that? Okay. Cosine pi, cosine looks like this. Cosine pi is -1. Cosine 0 is 1. So we have negative 1 become 1 plus 1, which is 2. So that gives us 2 a cubed over 3. Integral from 0 to 2 pi. Because we pull out the constant, so only 1 left. Well, that's like integral of theta. I mean, we get theta, right? Integral 1 is theta, so theta evaluate from 0 to 2 pi. We plug in 2 pi is 2 pi, we subtract plug in 0 is 0. So we have 4 pi a cubed over 3. Do we have the same answer? Yes, they match. Yay! So this is how we calculate triple integral in spherical coordinates. So far, so good, everybody. Let's continue. Example, let E be the parts of the solid ball, x squared plus y squared plus z squared equals 5, that lies in the first octet. Suppose E is made of materials with mass density mu equals x squared plus y squared plus z squared. Set up, but don't evaluate, a triple integral that represents the mass of E in each of the following ways. First, in Cartesian coordinates. Well, that's the same as the rectangular coordinates. B in spherical coordinates. B B is in cylindrical coordinate, and C is in spherical coordinates. Okay, so we usually use spherical coordinates if the solid is really like a ball or like a portion of a ball, right? Okay, but now let's set up all three of them, then you can compare and you can see the difference between them. Okay, so let's draw the picture. So solid ball lies in the first octant. So we have this ball. But we are only interested that lies in the first octant. Okay, so which is this piece? I mean this piece. Okay, but I just want to draw the base circle, and then it's easier for us to set up the intervals. Okay. Next, so A, we want to use Cartesian coordinates x, y, and z. Okay, so in this picture, I would do integral. Okay, and let's see here. And then our inside is x squared, y squared, plus z squared. That's the density function. Let's do dz, dy, dx. Okay, so I will do dx first. And this is a circle with radius 5, right? So we draw this small width, dx. And then next is dy. So we draw the rectangle on the xy plane. Okay, so here we have what is the bottom? So the bottom of this little rectangle, we have y equal to 0. The top of this little rectangle, we are on the circle. The circle of the xy plane is x squared plus y squared equals 5 squared. Oh, wait a little bit. Let me change. So I think I have a typo here. So let this be 25. So the then the radius is indeed 5. Sorry about this typo. Okay, so and then we have this circle. This circle on the xy plane means the z is 0. So then we have x squared plus y squared equals to 25. So y is, see, this is the upper half of the circle. So square root of 25 minus x squared. So x is from 0 to 5. And the y goes from 0 to square root of 25 minus x squared. So far, so good, everybody? Okay, now how about z? So pick any points on this rectangle and then go to the z direction. You can see the bottom. The bottom is like z equal to 0. But the top is on the sphere. So we solve for z in the sphere. Well, we have 25 minus x squared minus y squared. So that's 25 minus x squared minus y squared. So far, so good, everybody. Okay, so that is how we set up in Cartesian coordinates. Let's continue to look at how we set up in cylindrical coordinates. Sorry. Okay. Okay, so in the cylindrical coordinates, we have r, dz, dr, d theta. That's the volume differential. And for the density function, you see x squared plus y squared is r squared. So we have r squared plus z squared. Okay, you cannot still put x and y here because we don't use the variable x and y. Okay, so x squared plus y squared is r squared. So we place x squared plus y squared by r squared. This is our new density function in terms of r and z. Okay, and then we also look at the space. The space region is 1/4 of this disk, okay, with radius 5. So our theta goes from, well, this is the first quadrant, right? When we project it on the xy plane, so that's from 0 to pi over 2. And then our r is from 0 to 5, right? And then now still z is the bottom point of this region. Okay, so z is 0. The upper one z is on the sphere. But now let's express z in terms of r and theta. So x squared plus y squared is r squared. So z is 25 minus r squared. There. So far so good, everybody? Yes. Let's continue. Okay. See, spherical coordinates. With spherical coordinate, we have this. And the density, well, x squared plus y squared plus z squared. That is the rho squared, right? And what's the volume differential is rho squared sine phi d rho d phi d theta. Oh, my d looks like phi. Okay. So far, so good, everybody. Let's see. So this region, r still goes from 0 to pi over 2. Phi, see, is in the first octant. So the open drop-down angle is also from 0 to pi over 2, right? It's above the xy plane. And then our phi is now from 0 to 5. You see? Well, this is the easiest because they're just like all the variables, theta, phi, and rho, they're between two constants. Okay? All right, let's continue. So, by the way, please, after class, please go ahead and evaluate this integral. Okay, you should be able to do that. Yeah, integral of rho to the 4 is rho to the 5 over 5, right? And then you can integrate the sine phi. So please work on this integral and then find the answer. Okay, evaluate this integral after class. All right, let's continue. So let E be the solids given by the inequalities. X squared plus y squared plus z squared less than or equal 1. And then the other one, square roots of x squared plus y squared less than or equals z. So set up a triple integral that represents the volume of E in each of the three coordinate systems: Cartesian, cylindrical, and spherical. Part B, pick one and then evaluate. Okay, now let's draw the picture. Okay. So, let's see. All right. So, we have the sphere, right? This is a sphere with radius 1. Okay, and we have a cone. So a cone looks like that. Okay, so you can see the cone intersects the sphere and we get a circle. Okay, what is this circle? Well, in this case, it's better to, because we're gonna do it in the three different coordinate system anyway. So I'm gonna change this in terms of the cylindrical coordinates. Okay, because that is easier in this case. X squared plus y squared. So we want to find the intersection. Okay, so r squared plus z squared equals 1 and z equals r. So we want to solve for this system of equation to find their intersection. Well, we plug in the first one, right? And then we have r squared plus r squared equals 1. R squared is 1/2. R is plus or minus root 2 over 2. So if we project, let's see. Okay, if we project this guy down, this is root 2 over 2. Okay, and this is the base disk, base circle. Okay, now we're ready. So first, set up, okay, let's use Cartesian or rectangular coordinates. Okay, so what is that? Okay, because we want to find the volume is also 1 inside, and let's do dz, dy, dx. Okay, that's my habit. So what do I do here? Let me use a different color, then you can see what I draw on it. So okay, so let's do dx. So we look from the outside to the inside. Dx, x is from 0 to root 2 over, oh, not only 0, it's because it's the whole disk, so it's minus root 2 over 2 to root 2 over 2. Now, next is the dy. So we draw the rectangle like parallel to the y-axis. Then our y. So you know, this is on the, this is circle. This is the circle. X squared plus y squared equals to the radius squared, which is 1/2. Right? And then when we solve for y equals plus or minus square roots of 1/2 minus x squared. So the top one we have positive 1/2 minus x squared. The bottom we have negative square root of 1/2 minus x squared. That is the y. Okay, this is the x, this is the y. Now how about the z? The z is, so we pick any points on this rectangle and go to the z direction. See, it cross the solids and the surface of the solid in 2 points. The bottom one is on the cone. So on the cone, we get z equals square root of x squared plus y squared. The top point is on the sphere. So sphere is 1 minus x squared minus y squared. Okay. So this is the rectangular coordinates. So far so good, everybody? Okay, let's continue. So let's use cylindrical coordinates. Cylindrical coordinates. So V is then 1 r dz dr d theta. Okay, now let's see, what is that? Well, that is our theta is from 0 to 2 pi. Our r is, look at the base region. R is from 0 to root 2 over 2. Then z is from the cone. So the cone, z equals r. To the sphere, sphere is square root of 1 minus r squared. So far so good, everybody? Okay, let's continue. So this is cylindrical coordinates. How about spherical coordinates? Spherical coordinates. Let's see. I want to keep, okay. Let me do the spherical coordinate here, because we still need some space to solve the integral. Okay, spherical coordinates. Now let's see. We have 1, and then we have rho squares sine phi d rho d phi d theta. Right? Our theta is from 0 to 2 pi. Our drop down angle phi. Okay, now let's see. You see, our drop down angle phi is from here. That is 0 to. Do you know what this is? Okay, so what is this angle? Well, let me draw a picture here. So if we look at this guy, this is 1, right? And this is a sphere. It intersects the cone. So it intersects the cone. The cone is like x equals to z equals to r, right? Okay, and you can also see if the cone intersects the xy plane, intersect the yz plane, xz plane at the line z equals x and z equals y. Okay, so that's why this angle is pi over 4. So far so good. So this angle is pi over 4. And you can see that's why this length is root 2 over 2. Okay, and yeah, this is 1, and then that's the angle. So that is the angle is pi over 4. So drop the angles from 0 to pi over 4. And then how about our row? Well, the row is then from so that is from 0 to let's see, from 0 to 1, right? That is exactly the row. So the row is like here. So it's from it's right here. So it's from 0 to 1. Okay, and you can see this is the easiest to compute because all the coordinates has the boundaries constants. Okay, so let's compute it. So part B, you'll compute using the spherical coordinates. So first we're gonna integrate the row, right? We get rho cube over 3 sine phi, and then rows from 0 to 1 d phi d theta. Well, we plug in 1, we get 1/3. We plug in 0, we get 0. So we get 1/3. We can move it in front. And then integral of sine phi. Okay, what's integral of sine phi? That is negative cosine phi, right? Evaluate from 0 to pi over 4 d theta. Well, that is the same as negative cosine phi minus negative become pi plus 0 cosine, cosine 0, and then d theta. Okay, so evaluate, I plug in pi over 4 here. Subtract negative when we plug in 0. What is cosine pi over 4? So pi over 4, we have root 2 over 2 minus plus cosine. So negative of root 2 over 2 plus cosine 0 is 1. And then integral of a constant with respect to theta is just theta, right? Evaluate from 0 to 2 pi. That's the same as we multiply by 2 pi. So we get 1/3, 1 minus root 2 over 2 times 2 pi. We can also simplify and distribute the 2. We get 2 times 1, 2, then 2 and the bottom 2 cancel. We get square root of 2, and then times pi. So this is our answer for these questions. Okay, so now you can see, compare 3 types of coordinate system. Which one is easier? So if our solids is like a portion of a sphere, it's better to use spherical coordinates. Otherwise, you're gonna integrate like something like a square root. You probably need to use substitution, or well, if you're working with this, you probably need to use substitution, trig substitution, and more integration technique to solve the integrals. And more algebra are involved as well. Okay, So this is this example. Let's continue in the next video. Okay, see you soon.